2, 1, 0.
Hello, everyone. Welcome to another event and another session at ACE in the Commander Systems team. Today we have Sam. Sam is a PhD candidate at Brown University, and he is focusing on reinforcement learning and in the intersection between reinforcement learning and the Commander system with much more emphasis in reinforcement learning. Today we're going to talk about his paper RACT, which is toward amortized ranking critical training for collaborative filtering, and how we can use actor-critic in helping to re-rank and improve our collaborative filtering. So first of all, welcome to ACE. ACE is a machine learning, it's a community of machine learning practitioner researchers who have gathered around topics in AI research, engineering, and products. We host free live sessions 3 to 5 times a week, and we also provide premium content in various subject areas, and everything is on YouTube. If you ever want to interact with ACE and help out or present, there is a link in our ACE channel that can help you with that. So back to Sam. Hello, Sam.
Okay. Hey, thank you for that. So I'm going to today be presenting this paper, RACT towards amortized ranking critical training for collaborative filtering, that we presented at ICLR this year. It's exciting to present this to a group of people who like recommender systems. So this is work that I did in collaboration with Junyan Lee, who was at Duke while I worked with him and is now at Microsoft. So so this work, the quick summary of this work is it's using actor-critic methods from reinforcement learning to more directly optimize ranking-based metrics that we care about in recommender systems and collaborative filtering. Okay, so a brief introduction to the problem. We all know recommender systems. They are ways to deliver personalized subsets of items, maybe from an enormous data set of choices, to a user based on their preferences. Hey, did I lose my presentation? I'm sorry. Can you still see it?
Yeah.
It disappeared for me. This is technical difficulty. I'm sorry.
We're sorry about that. So we can still see it. So Chang is going to help us with this.
Oof. Okay.
That's fine.
Just give me a second. I'm sorry. I'm going to stop presenting and restart it because I can't see the slides on my screen. Okay.
He can't see the slides anymore.
No, but it's on my end. They just disappeared from my computer for some reason. Okay, and we are back, right?
Yes.
Okay, great. And I'm sorry about that, but now we're in the clear. Okay, so that's what recommender systems do. They deliver personalized subset of a maybe large amount of options to a user based on their preferences. Collaborative filtering is a way to deliver recommendations that's based on extracting patterns from a large amount of users. So an easy example of this is if you know that many people watch every movie within the Lord of the Rings trilogy, and a new user's seen 2 movies with the Lord of the Rings trilogy, you might recommend that they are also interested in the third one. So something interesting about recommender systems is that their use case is often to deliver a user a front page of content. So for example, on the screen that I have here, I'm far more likely to interact with something that pops up right when I pull up my browser on Netflix than anything else. So it's very important for a recommender system to get this front page right. And this is in contrast with other types of machine learning methods where maybe you're trying to learn how to properly score something or how to learn a regression task or classification task. This is a ranking task where we are interested in populating the first few items that we return to somebody with things we assume they're going to be interested in. So in this next part, I'm going to describe how we sort of evaluate these ranking losses and the difficulties that this brings up in optimizing these systems. So again, we're interested in delivering a front page of content to a user, and this is pretty important in how we evaluate our methods. So ranking losses are based on the order of the items that our system returns, not just the absolute scores it provides. It's less important, for example, to predict how many stars a user is going to give a movie than it is to say these are the 10 movies that the user is most likely to interact with. So generally, the way these systems work is we want to have information we know about a user, and then items that we know the user would be interested in that we did not tell our system about, and we hope to recover the items that the system did not know about through only the information that we did. So this usually involves, in our case, involves if we have a set of items that a user has interacted with, for example, all of the movies that they've seen, we take a subset of that and try to rank highly the remaining movies that we know that they're interested in. So how this comes across in our ranking metrics is, for example, a simple ranking loss is called a top K loss. What this says is, for example, in the top 100 loss, that we return 100 movies and we see how many movies that we know the user was interested in end up in that 100, and the more the better. Another example that is a little more involved, but also closer to what we actually care about, is called NDCG. This is the normalized discounted cumulative gain. And it's like a top K loss that penalizes you more for misranking the first item than it does for misranking the 100th item. Okay, so now on to why this turns into a difficult optimization problem. So the problem is that ranking losses, again, rely on the order of items that your model returns, but models don't naturally return orders, they naturally return scores. So an example of a model that you might use for recommending systems is something that scores each item in your data set and then sorts these scores sorts these scores so that the highest scores are first, and then tries to make it so that the ranking is similar to what we want. But if we look at this diagram on the right-hand side, and we look at the path between the user data that goes through the model and gets to the ranking loss, we see that there's a sorting component, and sorting is not a differentiable operation. So this means that all of the machinery that we usually like to use for complicated machine learning models in reference to gradient descent can't be directly applied to this problem. Okay, so there is a solution, a general solution that people use to this, which is defining a surrogate loss. So instead of the ranking loss, which is our final evaluation metric, I don't know why, I'm sorry, my screen keeps on disappearing. I really don't know where it's going. I'm gonna do this one more time.
That's fine.
Fixes. Thank you for your patience, everyone in the audience.
So for everyone in the audience, if you have a question about anything that is being presented, please share them in the chat and we will be relaying them to Sam.
Okay, I think I fixed it. We'll find out soon enough. Okay. All right, are we back?
Yes.
Okay, so I just described why ranking losses can be difficult to optimize directly because gradient descent can't be applied to them. So one solution that people have come up with to this problem is defining surrogate losses, which are differentiable functions, which hopefully have similar properties to the ranking loss. So optimizing the surrogate loss will give you better performance on the ranking loss. As we see in the diagram on the right, there's no sorting operation between your surrogate loss and your model, so you can pass gradients all the way back. So an easy example of a surrogate loss would be the mean squared error, which, for example, if you had a score for each item in your data set, you would try to return a high value for scores for items that you know the user's seen, and a low value for items that you know the user hasn't seen. Another example that I'll be talking about more later is called the negative log likelihood. This is calculated by turning your scores into a probability distribution, and then trying to make that probability distribution have a high probability of generating the user's interaction history. So these are ways that, although we don't care about the surrogate losses directly, optimizing the surrogate losses can give you improved performance on the ranking metric that you truly care about. Okay, so that is good to the extent that your surrogate loss maps well to your ranking loss. But of course, since they're not exactly the same thing, there is going to be some slack between the two. And optimizing one might not do as well of a job at optimizing the other as you might expect. So I just made a quick graphic of this difficulty. The height of the bars represents the scores you might score items with. You're hoping to get the red scores high and the blue scores low. And this just shows that it's possible to change your surrogate loss, which is the negative log likelihood, without updating your NDCG at all, which is the ranking metric. And it's possible to change the ranking metric without changing the natural log likelihood. So what this means is that although you might be optimizing one thing, you might not be making as much progress on the other as you actually hope.
Right. So just I guess like to clarify, the audience was asking, so there's two metrics in question here. One is, so for example, the NLL could be used to measure just like the scores of an item. So maybe a recommendation with the score of 0.9 is ranked higher than a item whose score is 0.4. Right. But what's important really is that the 0.9 is actually just, okay, it's rank 1 versus rank 2, but the score could be a bit off and still provide the correct ranking in a sense. Like the 0.9 doesn't have to be like accurate. It can be 0.8, which is still higher than 0.4. Right. But we have to measure that because it's differentiable.
Yeah, that's exactly right. So the point is that although it is better to score items that you know a user interacts with higher than items you know a user doesn't want to interact with, that is not really the whole story, because we don't care about getting the absolute number right. We don't care about saying they might rate this Netflix movie a 4.5 instead of a 4.3. We just care that they're more likely to want to see this one than another one. So that's exactly right. Thank you. Okay, so now I'm gonna get more into the contribution of our method. So on the left, we have a traditional collaborative filtering system, which you start with a user's interaction history, you output a score vector, and then you minimize some surrogate loss in order to get better score vectors. And again, the difficulty with this system is that the surrogate loss you might be optimizing may not be as close to the ranking metric you really care about as you'd want. So our method is an attempt to correct this. So we take inspiration from reinforcement learning, which deals with non-differentiable objective functions pretty frequently. And we take inspiration from a method called the actor-critic architecture. And what the actor-critic architecture does is, if you have a non-differentiable function, you learn the best estimate of it that you can with a differentiable function, which we call the critic. And then you can use the actor to, instead of directly maximizing the ranking score, you maximize the critic's estimate of the ranking score. And insofar as the critic does a good job of representing the ranking metrics that you care about, by maximizing its output, the actor is pretty much directly maximizing the ranking scores that we care about, which is the goal of this. So again, the actor is what's creating the scores, and the critic is what's going from the scores to an estimate of the metrics that we care about. And eventually, we're going to have the actor maximize the critic's output. Okay, so that was our contribution. I am going to take a step back, and I want to describe the method that we built upon. So this is a deep learning method for collaborative filtering, which adds layers of complexity, and certain recent research has showed that deep learning methods in collaborative filtering are sometimes not as powerful as we want, and can be outperformed by simple baselines. But the method that we were building on, which is called variational autoencoders for collaborative filtering, was a deep learning method that actually had pretty good, consistent, improved performance compared to simpler baselines. And the fact that we're adding a additional neural network layer on top of this neural architecture means that we needed to be really careful that our baseline was stable. So I want to just explain how this base actor method works. So the architecture that it uses is called a denoising beta variational autoencoder. I'm going to just break down these terms so we understand it a little better. An autoencoder is a deep learning extension to a latent variable model. The goal is to take in an input, compress it to a smaller latent representation, and then reconstruct the input from this compressed representation. So we have this summarized in the equation above. So first we create a latent vector z from the input, then we create a reconstruction from the latent vector, and then we have some reconstruction loss where we try to make the latent vector, the reconstructed input and the original input similar. Latent variable models are of course used in collaborative filtering pretty frequently in a linear sense, and autoencoders have shown good performance extending this to more expressive models. Okay, now the denoising part. A denoising autoencoder is something that tries to recover an input from a corrupted version of that input. So again, the way that we evaluate these, or the way that we try to predict a user's interaction history is by taking items we know they've seen, dividing them in two, things we tell the model about and things we don't tell the model about, and trying to recover the held out items from the ones we tell the model about. So denoising, which involves dropping out certain parts of the autoencoder's input, is a good way to represent that. And that's what I have highlighted here. Now for the variational part. Collaborative filtering is a method which relies on the idea that users occupy some shared structure of a latent space, and variational autoencoders make this explicit by enforcing the same prior, usually something like a normal distribution, on all of the users' latent representations. So this just fits with the ethos of collaborative filtering, where you know that users have shared preferences, and you're trying to map them to the same space. And this information sharing makes these methods generalize much better. And finally, the beta. What the beta represents is, although the equation I have above, without the beta, is the equation for a variational autoencoder. Variational autoencoders are generally used for generative modeling, where you're interested in being able to summarize a data set and generate samples from that data set. But for collaborative filtering, we're not so interested in the generative capabilities of these methods. So we can tune down the regularization that's caused by the KL divergence term in order to focus more on the reconstruction term.
Sam,
yes.
Quick question here on the denoising point. The question is that in a practical sense, like, could this help with the fact that, let's say, when users are clicking through things, sometimes they click through something that's kind of more of a tangent. And if the recommender system is able to, let's pretend those tangents are noises, right? Maybe they're really interested in one, let's say, like a toothbrush, but they are clicking through like tricycles or something. Like, despite that, they by including this denoising, even with some sort of change to the user's behavior, like, you would still be able to get to the true thing that they're interested in. Is that, in a practical sense, how this could help?
So that is one way this can help. The general reason for it is so that we have a target for our training method, because without some sort of dropout, we don't have any indication of items a user is definitely going to be interested in that the model didn't know about. So without the dropout, all we're doing is saying the user clicked on these 20 things, compress it and reconstruct it and try to get those 20 things back. So it can just learn an identity function in the worst case. And this dropout makes it so that the task is a little harder, and it needs to learn the behavior on one movie or one item from the others. But what you said is also true in that when you do this dropout procedure, you are training it on sort of a variety of different subsets of the user's history. So if there is an anomalous result, it's likely to not be in many of the subsets, and you can sort of learn which are the truly important items and which are just sort of the spurious ones.
Gotcha. Thanks. We have another question, actually, which is, if the generative component is not that important, why not use a regular autoencoder versus the variational autoencoder?
Yeah, so that's a really good point. And one of the answers to that question is that the way these methods are evaluated and the ones that stick in the literature are sort of plainly and simply the ones that do well, the ones that give us the behavior that we want, give us good ranking evaluation metrics, provide good front pages, and KL divergence is a regularizer that has proven to do well. So it's sort of an empirical question, what to set beta as, why to have a regularizer in the first place, and the answer is pretty much that. One of the answers is that it works a lot better than not doing it. So this method tried a variety of different regularizations, and KL divergence was the one that worked the best. So that's one answer, and then the other answer is again that it sort of fits with the ethos of collaborative filtering, that you want your latent space to have some sort of shared structure. Because if you don't have this sort of regularization, then if your neural network is expressive enough, then it can sort of learn totally independent representations for each user that don't really share any of their information. So it can be maybe over-parameterized or over-expressive. And collaborative filtering is a problem where the inputs are actually very sparse and you're sort of working in a low information domain. So having these priors and these regularizations is pretty important. Gotcha.
Thanks.
Great. Okay, so that sums up the work that was not ours. And now to move on to what we did. So again, that was a way to train a model with a surrogate loss function to create pretty good item scores. Our contribution is to turn this surrogate loss function, instead of using the surrogate loss function, to more directly use a loss function that represents the evaluation metrics we care about. So again, the way we do this is by having a differentiable critic model that goes from the actor's outputs. Again, that's the scoring model. And you pass them through this differentiable model, and you get an estimate of the ranking score, which you try to make it as accurate as possible. And then once it's accurate, you can propagate the gradients from your estimated ranking score back to the model to improve the model's predictions. So in order for the critic to work, it needs to use the same inputs as your evaluation metric. So the inputs that the evaluation metric needs is it needs the item scores, it needs the items that the user interacted with that the model was told about, and then it also needs the targets, which are the items that the user interacted with that the model was not told about. So these are the three inputs that are necessary for a critic model. So the easiest thing to do would be, we have a neural network, which is our critic. We have all these big vectors, so we could just concatenate them, pass them through the neural network, and get a ranking score. But the difficulty with this is that task is the same as saying we have this huge 60,000. So let's say there's like 20,000 items in a data set. That means that the concatenated vectors will have 60,000 features, largely sparse, and we're trying to map that onto a single number, which is sort of just an impossible task to expect from your neural network. So we need some sort of simplification to this problem. And the way to do that is to do feature extraction, which hopefully gets the sort of important behavior from these three features without being sort of too large of an input for the critic to work with. So that's what we have here. The features we extract are the negative log likelihood, which I talked about before in a little more detail, and it is a metric that sort of captures some of the behavior we want for a ranking function from scores. Then also the count of observed items that we pass to the model, and also the count of unobserved items that we are sort of trying to recover. So I have slides a little later to clarify the relationship between these three things and the NDCG. But I do want to go into why we made these choices, because you might notice that the only path between the ranking score and the scoring model is through the negative log likelihood. So it'd be a reasonable question to ask, why is this any better than just minimizing the negative log likelihood? Why go through this whole complicated critic procedure? So the reason is that the negative log likelihood, and again, I have slides that sort of visualize this a little better later, but the negative log likelihood doesn't map very cleanly to the ranking score. One problem is that in different domains of the negative log likelihood, for example, item scores that are sort of well sorted versus not well sorted, the ranking score might be very different in sensitivity to changes in the NLL. So for example, big changes in the NLL might not really affect the ranking score very much in certain domains, but small changes in the NLL might have big effects on the ranking score in other places. And we would want to focus our model's limited capacity on improving the ranking score where we can do it with just small updates to the model. And having this mapping really makes this a lot easier. And a similar thing holds for the other two features, where the scale of the negative log likelihood is really dependent on the number of items that the user's seen and the number of items that we're holding out. So the model might try to spend a lot of its modeling capacity changing, for example, users who have seen many items because their negative log likelihood is just naturally larger, even though this doesn't improve the ranking score very much. And so we might waste a lot of modeling capacity on a very small number of users and end up ignoring a large number of other users just because they haven't interacted with as many items in the past. So I know that slide was a lot. I'm super happy to take questions about that now or at the end.
I actually have a question. So
yes.
The inputted items and held out items, the summation of these two are always constant in each data set, right? So what I mean is if you said you have 20,000 and you interacted with only 100, then you have 19,900 basically in left out. So the summation of these two are always constant. Why do we input the two values? Why can't we just input one value? Okay,
that's a really great question and something I should clarify. So the inputted items are the items that the user has interacted with. Is some of the items the user has interacted with. The held out items is some of the items that the user has not interacted with. So let's say user A has interacted with 200 items in total. The inputted items might be 150 of them, and the held out items might be 50 of them. But then user B might have interacted with 2,000 items. So the inputted items might be 1,500, and the held out items might be 500. And this ratio is not always fixed, so it's sort of important to know both of these inputs in order to properly rescale the effect of NLL on the ranking score.
Okay, that makes sense. So you sample items from the inputted items and you sample from the held out items, and you just represent these two numbers.
Yes. Can you say that one more time?
So basically, you take samples of the inputted items and you take samples of the held out items, because passing it all of the held out items or all of the inputted items is just going to be too much for the model to make sense out of. Is that right?
So what you do is one of the although it's important to know exactly which these items are, sort of the most important thing is to know the size of these sets, how many input items there were and how many held out items there were. So what we do is we count the number of inputted items and count the number of held out items, and that's the thing we pass in.
Okay. We got another question, which is, what is the baseline ranking score for the critique model?
So correct me if I'm wrong, but I assume that means what is the score that it is trying to represent. You can choose whatever ranking metric you sort of want to work on. The one we did was the NDCG. So the normalized discounted cumulative gain is the thing we're trying to represent given these three numbers.
Just out of curiosity, how would the mean reciprocal rank? Wouldn't that work?
What was that? I'm sorry.
The mean reciprocal rank, MRR.
Oh, I'm not actually sure, to be honest. Okay. But I assume if it sort of has similar behavior, then yeah.
Okay. Awesome. And I know this is taking it a couple of steps back, but can you again recap about the denoising part, because we have some questions about it still. So denoising basically simulates predicting future interactions. Is that? But how does it happen?
Right. So this is an implementation choice. There's lots of ways that you can divide a user's interaction history in order to make predictions about them. One way is to maybe try to predict. Let's say they have an interaction history. You take the first 3 quarters of their interaction history throughout time, and you try to predict the last quarter. Mm-hmm. That's a totally valid way to also do this. The way that we did it, and the way that the paper whose actor we built upon did it, is they took random subsamples of the user's interaction history and tried to predict the remainder of the interaction history. And this is nice because it sort of gives you a more robust data set, because there's many samples you can take from the same user.
Okay.
Did that get at the general thrust of it? I can sort of.
So basically, just to be clear, so this is just basically we're hiding some of the actual interactions to be able to learn from the other interactions and predict those ones, right? So it's technically you're masking them off for testing.
That's exactly right. That is the purpose of the denoising part, and it's some sort of denoising in general is just a good fit for collaborative filtering problems. Certain methods, my impression is more in the past, certain methods would not do this step. It would just be the autoencoder part, and they would rely on the compression of the autoencoder in order to extract these patterns. So they would map an entire user's features, entire user's interaction history, and try to recover the entire interaction history. But denoising seems to be a better fit to the problem, because in real life, you don't know every item a user will interact with. You only know a subset.
Okay. So we can continue for now. We don't have another question. I'll let you know if we do.
Awesome. Okay. All right. So I described the general setup of the critic. The point of the critic, again, is to provide high-quality gradient signal to the actor, to your scoring function, so that your scoring function can directly maximize your estimate of the evaluation metric. So this is a two-component training procedure, and that means there's sort of 2 possible places for failure. I think something people might be more familiar with is how difficult it is to train generative adversarial networks because of the same sort of 2-component interaction. This problem is slightly less complicated because it's not adversarial, but it suffers from some of the same problems. So the 2 places that this can fail are if the actor doesn't provide good inputs to the critic, and if the critic doesn't provide good gradients to the actor. So an example of the actor not providing good inputs to the critic are if all of the actors' scores, if your scoring model is just doing very badly, then your ranking metrics are all going to be almost uniformly 0 for every user in your data set. If you're misranking everything, then your ranking metrics are all going to be as bad as they could possibly be. And this means that the critic won't really be able to extract much useful information by mapping all of the actors' predictions just to 0. So the actor needs to sort of be a certain level of good in order for the critic to even be able to do its job. So the way we do this is, before anything, we just pre-train our actor. And luckily, since our actor is just a surrogate loss function method from prior work, we just use their method for pre-training our actor. So that's the first step. And then when that step is done, we hopefully have a decently good baseline actor that is providing useful inputs to the critic. But the critic at this point is totally untrained, which means that any gradients we would get from it wouldn't really mean anything because its output is not yet tuned to the ranking metric that we care about. So now we need to pre-train the critic. So by doing this is we generate a bunch of actor outputs and we pass them into the critic. And then we try to map that as closely as possible to something like the NDCG. If this works well, then the critic estimates the NDCG closely, and then taking gradients against the critic will maximize this estimate pretty well. So that's phase 2, is just critic pre-training. And now for the part of our method that actually improves our ranking outputs, we update the actor, we pass in users to our actor, and then we get a estimate of the ranking metric from our critic, and then we can update our actor to maximize the critic's output. And so this, if the critic is doing its job properly, will also maximize the true ranking output. And then since the actor is changing, that means that the critic sort of needs to adapt to a new domain of inputs from the changing actor. So we need to retune the critic slightly in order to keep up with the changing actor. So there's this actor-critic iteration where we update the actor to maximize the critic, and then we update the critic to be accurate given the updated actor.
I have a question about that. So basically, can I say that the first part is optimizing the actor by itself, and that is by a random model? It could be just normal matrix factorization, for example.
Yes.
And then the second part is taking the output of the matrix factorization, and then you are training the critic part by itself. And then the third stage is updating both of them.
Yeah, so that's right. So but you're not updating the actor the way you did before. The way you were doing before was just like training against your surrogate loss or however your model was working.
Yes.
Now you're updating the actor to maximize the critic's output. So the critic's output should be an estimate of a ranking metric. So maximizing the critic's output should maximize your ranking metric, which is what you want.
So the third stage is basically maximizing the critic, but it doesn't really affect the actor trained hyperparameters, for example. Actually, no, it does affect the actor's hyperparameter, but not the critic's hyperparameters.
Yeah, so that's exactly right. So it updates the actor's parameters in order to make the critic's output higher, which is as close as we can hope for to making the true ranking metric higher. Mm-hmm. And then it just retunes the critic to still be accurate, given the change. So
I'm sorry if I don't get it fully, but why can't we merge step 2 with step 3 then, right away? Like we have a basic actor pre-training, actor model, and then we can just start doing the actor-critic iteration from that step right away.
Okay, that's a great question. So the reason for this is because the critic is initialized to just like a random neural network, which means that so the whole point of this is to get good gradients from your critic. But if your critic is just to start a random neural network, that means that it's not really representing the evaluation metric like NDCG very well. It's just taking in an input and maybe outputting noise. So that means that if you try to maximize it, you would really just be trying to maximize noise. It's only a helpful step if the critic is telling you something interesting. And for the critic to tell you something interesting, you need to have pre-trained it to map onto the metric that you care about.
Yeah, that makes sense. Thank you.
Great. Okay. So that is the training procedure that we go through. I think next is results. Yeah. Okay. So these are the results of our training procedure. I'll focus mostly on these bottom graphs. So the black line is just training our scoring function using something like a surrogate loss. And our red line is when we start the actor-critic iteration training scheme. So the red line is our addition to a generic actor. And as you can see, once we start training with the generic actor, which tunes our scoring function to the ranking metric that we care about, we get a pretty big performance increase. And I'll show this a little later, but this was true on a variety of
Hello?
So yeah, I think Sam is having internet connection problems, so we'll just wait for him till he comes back. Hopefully it's not going to take too long. So yes, this is the time if you have any questions. I know Serena asked a question. We'll ask that to Sam once he's back. But if you have any other question, please post it here in the channel. If you want to watch more of our videos, ACE channel has all of the videos that we have recorded before, and it contains various topics about machine learning. So please check them out. Okay, so far, just as a recap for what Sam has been talking about is they have been, so Sam and his the co-authors, what they have been doing is they're trying to build upon the variation autoencoder's paper, but not to score items properly, but actually to rank them properly. So they're optimizing on the ranking more than they're actually predicting the scores, right? So if I predict a score to be 0.9 for an item that I have actually interacted with, or 0.8, it doesn't really matter. What it matters is what part of the recommendation, what part of the ranking is it observed at. So to do this, they build upon the variation autoencoder paper with another additional step, which is the critique method. So the actor part is exactly the same as the variation autoencoder, but now they are introducing the critique part, which is trying to optimize the output of the variational autoencoder to actually do proper ranking. So in this step, what he was talking about the 3 stages. So stage 1 is just training the variational autoencoder by itself, and then it's pre-trained. So it has some initial weights and initial parameters. And then the second stage is taking blindly the output of that variational autoencoders and by itself training the critique method. So they're trying to re-rank the output of the critique. Now that we have a pre-trained actor and a pre-trained critique, what the third stage is they're trying to actually train the actor and the actor and the critique iteration. So what that means is, given the output of the actor, the critique gives a score. Is it a good score or not, using the NDCG? So given that, if the score is low, it goes back to the actor and it changes all the weights to be able to do a better recommendation and a better output next time. So in this third stage, what's changing is not actually the critique at all. The critique is just used as an evaluation, but what is changing is the actor part itself. I would like Susan's. So Susan is the reinforcement learning stream lead. I would want to see if she has anything to add.
Yeah. So sorry, I also disconnected briefly because we had like this fire, whatever test thing.
Oh
But okay, so I'm so sad that I missed a bit of it, but I did, I guess, look at the slide beforehand. I think what's like clever about this is, I guess, what we mentioned before about, so, oftentimes it's easier to be updating gradients because, like, if you're outputting the scores of how important you think an item is, that is, like a more differentiable way of, well, that is differentiable, and it's like a easier way of training because you can back propagate with gradients. Whereas the real problem is like the rank itself. But then, you also want to not have it be exactly like a classification problem per se, right? It's not like, oh, this is like 1 or 2. And then, okay, I see Sam is back. But hello?
Sam, we can't hear you, unfortunately. I think the sound has something. Yeah, now we can.
Okay, great. Sorry, guys. Where did I lose you?
So basically, you were going through the results, but before that, I have a question to you that was asked twice actually, which is the loss function at each step. So stage 1, stage 2, and stage 3. What are the loss functions that you're optimizing on?
Great. And once I bring this screen up.
Take your time, and technical difficulties happen, especially during the pandemic where there's a lot of traffic. So yeah.
I gracefully finished my presentation through what I thought was no questions while we were lost. So, okay, so we were here. I assume you lost me like right around here.
Exactly.
Okay.
But yeah, like just if you don't mind recapping what loss functions for each stage, that would be great.
Okay, yeah, sounds good. So the actor pre-training step, the loss function is just the surrogate loss that I described before. So that would be something like the negative log likelihood, and that pre-trains the actor to do decently well. That loss function only updates the scoring function's parameters. The second one is the critic pre-training. This only updates the critic's parameters, and this takes a frozen actor, wherever it was pre-trained in the past. It takes the frozen actor, and it tries to map the frozen actor's outputs to the NDCG as closely as possible. So the loss function here is the mean squared error between the critic's output and the true NDCG. And minimizing this means that the critic's error will be, the critic's output will be close to the NDCG. The third thing is actor-critic iteration. Here, the critic's loss function stays the same. It's still just trying to stay accurate, but the actor's loss function is no longer the surrogate loss. The actor's loss function is now maximizing the critic's output. So it's, I guess, the negative critic's output. So instead of a simple loss function like a mean squared error or something, your loss function now becomes the output of a neural network, which is complicated, but gradient descent makes it work.
Sorry. So just to be clear, this means that we are still trying to score the maximum NDCG for the third step?
Yes.
Okay.
That's what the actor is trying to do. It's trying to maximize NDCG.
Exactly. Okay.
But yeah, I think I was gonna mention just before, I think this is a really cool way to map from the other metrics in typical collaborative filtering to metrics that are more rank focused, like NDCG. Like I know Omar, you had another point about like MRR, but we can discuss that after too. But yeah, thanks, Sam.
Awesome. Yeah, and it's and the hope is that this method will become more robust, sort of the better the features are. So improve surrogate loss functions, or maybe multiple surrogate loss functions as features. There's all sorts of ways to extract even better information from the scores that we didn't really explore that will hopefully make it an even better mapping to what we really care about. Okay, so I guess I'll just start the slide over and go through it briefly. But here we have the performance increase from our method. This black line is essentially what happens if we only do phase 1, which is training the actor on a surrogate loss. And then this red line is what happens if we start training on our learned loss function, which is the critic's output. So we see that once we start training, which is the third step. So we see that once we start training on the critic's output, we get a pretty significant performance increase on all 3 of these data sets that we tried. And we ran this with multiple seeds to make sure it was sort of a robust result, and we always get similar performance in terms of how much it increases the base actor. Okay, so I said before that that neural network methods in collaborative filtering can sort of be a finicky thing, and you really need to sort of drill down to make sure that what you think is happening is actually happening. We wanted to make sure that our critic's output was actually doing a good job of representing the NDCG. So on the left here, we have the NLL's relationship to the NDCG in a scatter plot. And you see here that the correlation is pretty low. And what that means is that the negative log likelihood can vary a lot while still having the same NDCG. And optimizing one might not be as close to optimizing the other as you might like. On the other hand, our critic's output, which is trained to be as close to the NDCG as possible, has a very high correlation of more like 0.85. And so what this means is that you can be reasonably confident that when you try to maximize the critic's output, you also end up maximizing the NDCG. Okay, so then after that, we did an ablation study just to make sure that our choice of features was sort of reasonable. We tried dropping out all of the counts, sort of one count, then the other, and then both. And we see that the red line, which uses all the features, performs better than either of the features on their own, and much better than with neither of the counting features. And given what we saw in the last slide, this makes sense because if your only feature is the negative log likelihood, and the negative log likelihood doesn't have a very good correlation with the NDCG, using something that only takes the input of one won't do a very good job at mapping to the other. And the final thing is we wanted to make sure that it wasn't just a simple architectural choice that gave us these results. So we tried a variety of architectures for our actor, as well as a variety of surrogate loss functions as our features. And we found a strong performance, or we found performance increase using all of these combinations. So that gives us decent reason to believe it's a pretty robust result. Okay, so that is the results, and I just want to very briefly summarize the high-level point of all of this. Recommender systems are sort of a difficult problem, and one of the reasons this is true is because the thing we care about is how to rank items, and this is a pretty hard thing to get a model to directly optimize. So our method was a way to use actor-critic methods to optimize this as closely as possible. And by learning a differentiable representation for the evaluation metrics that we care about, we could end up getting much better performance on the things we actually wanted to do. So that's it. And thank you guys for bearing through a variety of technical difficulties, and I hope I'm still presenting.
You are still presenting,
Right.
Yes. Okay. So for everyone in the audience, please ask any question that you have in mind, and we will relay them to Sam. So we have actually a question which is talking about the results. So is the result basically the average of over multiple runs, or is it randomly selected result?
The results are averages. Let me go back to this. These results are averages over multiple runs. Both the graphs at the bottom and the run and the performance increase on the top. These are, and then these two are just on a single run of both because they were, I guess, less central to the argument that we were making. These were just studies to see what was going on. But these results were based on multiple data sets and multiple seeds. Awesome.
Okay. I think there was a question in the beginning, which is how large can beta be in the beta denoising autoencoder?
How large can beta be? Okay. So this is going from memory a little bit, but the original variational autoencoders set beta to 1, and that is the way to sort of get the perfect generative model. The way that we set beta in this paper is essentially it's a hyperparameter. We know that it's going to be somewhere between 0 and 1 because we want to focus less on generation and more on reconstruction. And I believe the optimal beta was around 0.2 for all of these data sets.
0.2. Okay, so this means that it's way more reconstruction than it is generated.
Yes, that's
okay. That makes sense. Okay, any other questions? I think like the best part about this presentation is I already had like 6 questions and you tackled all of them without me asking any. So that was a good presentation.
Good to hear.
If there's any question from the audience, please ask them. Susan, if you have any question as well, go ahead. Okay. So since there's no any questions,
I guess one last thing is that the code is online, which and that's my GitHub account, and feel free to post any questions on the GitHub, and hope people play around with it and everything like that.
Awesome. Are you planning still to work on reinforcement learning and Nexus domain, like that intersection?
I have some interest in sort of expanding this general domain of use case. My interest has sort of more shifted towards like true reinforcement learning domains, like continuous control. But I am interested in talking about this stuff still. So awesome. That's sort of what I said. Yeah.
We'll be waiting for the new work.
Yeah, definitely.
Awesome. Well, thanks everyone. Thank you, Sam, for presenting. And again, we're sorry for all the technical difficulties, and we're really glad that we're still having you. So thanks everyone, and it was fun. Thank you, Sam.
Cool, guys. Thank you so much. I really had a blast.
That was my pleasure. So, okay. So Chang.